Okay, so we've saved one of the biggest proofs for last here. We are trying to prove that when two circles intersect, the line joining their centers bisects their common chord at right angles. So we're in essence trying to say that we're trying to prove first that OA is perpendicular to BC. So they are joining at right angles, and that BD equals to CD. Now, there's going to be a lot of writing. If you want, you can pause the video and try it on your own first. But I've broken this up into 2 bits here because we have just to give us a lot of space to write out this proof. Now, there's a few things you can see that have been joined here. So OB has been joined, O has been joined to C, A has been joined to C, and A has been joined to B here. So we've made 2 triangles here, and we want to first prove their congruence before we do anything. So I'm introducing these ones. So in triangle OBA and triangle OCA, we know that OB equals OC. These are equal radii. We also know that AB equals AC because they have equal radii as well. We also know that OA is common. Now, because we have these 3 things, we can make a statement about their congruence. So we can say, therefore, triangle OBA is congruent to triangle OCA. And that is side, side, side. Now, since we know that these 2 are congruent, we can make a conclusion about 2 angles. We can also say, therefore, triangle angle BOA is equal to angle COA. So, BOA, because they're congruent triangles, is equal to COA. These are the same size. We'll get to that in a moment. Okay, now, the reason for this is we have corresponding angles in congruent triangles are equal. Okay, now we're going to say in triangle OBD and triangle OCD. So we're looking at 2 new triangles now. We're looking at triangle OBD, this one here. So not that big triangle before, but OBD and OCD. We are looking at those ones now. So triangle OBD and OCD, we can say that OB equals to OC, and these have an equal radii. We can also say that, like we found before, BOD, angle BOD, is equal to angle CDO. Oh, sorry, BOD equals COD, apologies. So we needed this, it was proved above, sorry. That's why we did this random congruence proof before up the top here, because just looking at these triangles, there's not enough given to us to just assume that these 2 are the same. We needed to prove the congruence on these dotted larger triangles and then use the fact that corresponding angles in congruent triangles are the same to make this link between these 2 angles. We couldn't have just done this right off the bat. That's why we took that extra step in proving their congruence. Now, those 2 are the same, and we can also say that OD is common. We can pretty clearly see that from the diagram. OD is common. That gives us enough to say that, therefore, triangle OBD is congruent to triangle OCD by side angle side. Okay, so we're almost there, but let's just pause and just look at what we've done. Because we're trying to get to this, okay? We're trying to, at the end of the day, prove that OA is perpendicular to BC. So we proved the congruence of these two first, then we proved the congruence of OBD and OCD. So we're working our way through, we're almost there. We're going to say now that since those two are congruent, we can say that triangle BDO is equal to, angle CDO. So BDO is equal to CDO. So this angle is the same as this angle. And the reason, our corresponding angles in congruent triangles are equal. Okay, now BC is a straight line, okay? So let's actually just make a note of that. BC is a straight line. Now, because it's a straight line, the angles on it have to add up to 180 degrees. Now, if those two are exactly the same, then each of them must be 90. Now, I'm just going to rewrite that. So angle BDO added with angle CDO equals 180 degrees, because the angle sum on a straight line is 180 degrees. Therefore, BDO and CDO must be the same. So BDO will equal CDO, they're exactly the same, and they are both 90 degrees. That's the only number that adds to itself to give 180. Now, because both of those angles now are 90 degrees, we can say that OA is perpendicular to BC because they're both 90 degrees. Two angles are 90 degrees. One last bit here. We can say, therefore, that BD equals CD. Now, reason is the perpendicular from the center of a circle to a chord bisects the chord. So we're drawing on a lot of previous circle theorems to make this final proof. That's why we've left it right at the very end, because we're drawing from a lot of the congruence we've been doing, as well as a lot of the previous circle theorems. So that then, because the perpendicular from the center of a circle to a chord bisects the chord, then we can say that BD equals to CD, and hence we can say the line joining the centers bisects the common chord at right angles. So we have proved this last, arguably trickiest theorem here. If you watched all the way to the end, I know it was a long proof, so I really do appreciate it. But that brings us to the end of circle geometry. Thank you so much for watching, and I'll see you next time.